We are recording. Hello. Okay. Let's just introduce ourselves really quickly. Hello, I'm Sergio Garcia. Anyone go next?
Yeah,
Okay.
me.
Go ahead.
Alexandra Parra. Yeah.
All right. And my name's Lordson.
And I'm George Sunti. So let's get this video going.
Yeah, perfect. Okay, so we're 4 in this group. Let's just get started on chapter 4 questions. I'll read it out loud and then we can discuss. An elevator is being lifted at a constant speed by a steel cable attached to an electric motor. There is no air resistance, nor is there any friction between the elevator and the walls of the elevator shaft. The upward force exerted on the elevator by the cable is, and then we have our options right here. Anyone want to come for this one? Anyone want to?
Yeah.
All right, go ahead. Floor is yours.
So we have to take into consideration that the vertical forces of the elevator are the force due to weight of the elevator, which is equal to W newtons downward. Acceleration, we know it's constant, so it's 0. And velocity is constant as well. So we can say that the force would be that the force exerted on the elevator will be equal to the force of gravity, because both acceleration and velocity are 0.
Yeah.
So it's in equilibrium.
Yeah, precisely. Equilibrium, because the forces are acting at the same magnitude. All right, yeah, so if there's no acceleration, it's at equilibrium. We see that question is right. Good job, guys. We can hop on to the next one, 4.2. Now the elevator is being lowered at a constant speed by a steel cable attached to an electric motor. There is still no air resistance, nor is there any friction between the elevator and the walls of the elevator shaft. The upward force exerted by the elevator, on the elevator by the cable is what?
It would be the same concept, just different direction.
Exactly, just in the opposite direction, I believe.
Exactly.
Yeah, so again, just hammering in the idea that it's equal and opposite. Were you gonna say something?
No.
Okay. Yeah, so general.
Wait. Hold on real quick. You said it's equal to the force of gravity again, but isn't this time it's being lowered this time, right? And so it's being dropped.
Think about the y-axis being reversed. It'll be the same concept, same idea.
Yeah.
Just
whether going up or down.
It's still a constant speed. There's no acceleration. So the forces acting upon it are equal because there's no change. If it's not moving, or if it's moving at a constant rate, because if something's not moving, it's moving at a constant rate, but that constant rate is still just 0. So it doesn't matter what the number is. If it's moving at a constant rate, it's at equilibrium, which means that the forces are equal.
Would be 0. Yeah, so
and also anything having motion on the y-axis always has gravity acting on it too as well. So that's another point. Okay, I get that.
Yeah.
All right, so we got that correct. Yep, equal to the force of gravity. Now we're looking at a graph. The graph to the right, so this one right here, shows the velocity of an object as a function of time as it moves along the x-axis. Which of the graphs show the best, below best shows the net force versus time of the object. So we see here that the y-axis is x, right?
And
so
that's velocity.
Yeah, its slope would be. So, and then this is time. So it's asking us which best shows the net force versus time of the object. Anyone want to tackle this one?
You go ahead and tackle
it. Okay, so we're looking at it. We see our examples right here. Force exerted on the object would typically correlate to, if it's staying in a position, that most likely means that the force is is 0 essentially, because it would be not moving. So if I had to guess, I would say it would be E, because we see here it's no forces, it's constant, then it has a change in position. This is where we see that the force is higher, and then we go down and this. But if anyone has a different answer, I'd be interested to see.
Yeah, I think it's the same as you do. And also reminds me of a problem that we saw on the physics lab. It's the same. Like when you do the experiment, you see that when the force is constant, it's equal to 0 to the x-axis, and then when when it increases, it goes up like exactly that graph that we see on E.
Exactly. I thought the same thing when I did this question. And another cool thing that I noticed that helps me out is actually looking at the points where the slope changes. So you can see on the example given, it's constant, then it changes, and then it's constant again. So there's two of those pivotal points. I'll be looking for those two of those pivotal points in whatever chart I'm looking for as well.
Yep, I agree with you guys on that.
All right, perfect. Now we can check and see. And we were correct, it's E. All right, now we can move on to 4.4. A horse is hitched to a wagon. Which statement is correct? So I'm going to read through the statements and then we'll like popcorn in. So statement A says that the force of the horse the horse exerts on the wagon is greater than the force that the wagon exerts on the horse. The force of the horse exerts on the wagon is less than the force that the wagon exerts on the horse. The force that the horse exerts on the wagon is just as strong as the force that the wagon exerts on the horse. And then the second to last answer is the answer depends on the velocity of the horse and the wagon. And the last answer is the answer depends on the acceleration of the horse and the wagon. Anyone want to tackle this one?
I feel like it's most likely either D or E. I wouldn't say, the reason I go automatically for D or E is because in the question, it didn't say whether the horse is moving or not. It just says the horse is hitched to the wagon. So that kind of had me a little confused there. If it was speaking on force as in to get it along, we know, for you to move something, it has to have a net force in a direction, right? So I'm guessing that I want to say D, since it depends on the velocity of the horse and the wagon. I might be wrong, but
I think that's honestly, I think you're like, I like the direction you're going because it doesn't say whether the horse is moving at like a constant rate or not, like if it's accelerating, it doesn't really say.
Yeah.
I guess like if I was on a test, I might assume that it's not moving, but it just doesn't say. Does anyone else have any thoughts on this?
If the horse is hitched to the wagon and it's not moving and there is any kind of tension between the hitch and the wagon and the horse, then it would be in equilibrium. So it would be net force of 0.
That is true. So if
I would go for C on an exam just because it doesn't explain it's moving. It doesn't say if it's constant or variable. So I would stick to equilibrium.
Yeah, I agree. I should have went for that too, considering it's just equal. If it's not moving, it means they have the same amount of net force.
Exactly. How you said, I would go for D or E first, but then it's like,
that's exactly it. Like if it like said like they're stationary, then C is like the layup like answer.
Yeah.
But like since like it's a very vague question, like D and E like are compelling me. I do think final answer, like if I was on a quiz or test, I would put C just because I feel like that's like what we've been learning. So that'd be the safest guess.
Facts.
But
what do you think, Maria?
I do think it's C because if we take into consideration the action reaction law, and since it doesn't specify if it's accelerating or if it's stationary, we can say that the force that the horse exerts on the wagon is just as strong as the force that the wagon exerts on the horse. Because it's a big question, and C is, I think, the most logical answer to that.
I would agree with you. So if we're unanimous on C, we can now check our answer. And it's C.
Agreed.
All right, so the question was assuming that the horse and wagon are just like either standing still. Like that's what I would assume. If they just say that, like I'm just assuming the horse is just standing there hitched to the wagon. So we were right in assuming that. We picked the safe bet and we really used your critical thinking skills there. So great job. Now moving on to the next question. A lightweight crate notified by A and a heavy crate notified by B are side by side on a horizontal floor. You apply a horizontal force F to crate A. There's a friction between the crates and the floor. If the two crates are accelerating on the right, and then it goes on to different things. So it says if the two crates are accelerating on the right, crate A exerts more force on B than B exerts on A. If two crates accelerating to the right, crate A exerts less force on crate B than B exerts on A. If two crates are accelerating to the right, crate A exerts as much force on B as B exerts on A. And if two crates are accelerating to the right, the answer depends on the details of the friction force. And the final one is if two crates are accelerating to the right, the answer depends on the magnitude of the acceleration.
I'm leaning towards A on that one, but I want to let somebody else try it.
So I think we have to take into consideration that the acceleration for both, it's the same or like constant. And frictional force that we see on crate A would be less than crate B. So the content, like the contact for both, we do see that it's equal, but in opposite direction. So I would say it's C.
I agree. I agree with C. Reason why is because of the two objects in contact versus A and B. Sorry guys, I had to put a timer for 10 minutes just so we more or less knew where we were at. Because the contact between A and B is horizontal, and the force horizontally is affected by the static friction and the kinetic friction. It doesn't really say if it was in place, if it started to move. It says accelerating to the right. Yeah, so accelerating to the right, that's the force that's acting upon it, not the weight stuff.
So we can assume that yes, I would assume that these were originally static and that they're beginning to move, or not that they were always accelerating. Yeah, because this is the apply force. So let's just assume that they were standing still. So one thing that I think Maria said is that the coefficient of friction for A would be different for B, because A is lighter. And then on top of that, between the two forces, A is getting acted on, and then B is resisting that force. I would go with C. But was that the general consensus? Was it C?
Yeah, the way I thought about it when I did the question was just like, if I pushed on a wall with a brick behind it, how hard would I have to push on the wall to move the brick?
Yeah.
Same thing backwards. The same, you'd have to push the same force.
So I guess we can do that. Lordson, you said A, and I kind of
at the beginning, at a glance, but I do
sure.
agree on C. I was just going off of just the thought that if it were standing still and you need to move it, you'd have to exert more on B, using that force for them both to move to the right. But I agree with you guys on C.
All right, so we're gonna look right now, and it is C. Do you guys want to continue chapter 4? Or you guys want to try some chapter 5 questions?
We could do just one more question on this. Actually, I would love to go over it with you guys. Question 13, if you can.
Question 13, absolutely.
Yeah, I feel like it's one of those.
Let's see if we can find it. Okay, we found it. Oh, okay, this is one of the polling ones.
I had a little bit of an issue with it at first. I was able to get it down, but I think it's an interesting question to go over.
All right, I'd love to look at this. So a woman pulls a 6 kilogram crate, which in turn is connected to a 4 kilogram crate by a really light rope. So the weight of the rope is negligible. The light rope remains taut compared to the 6 kilogram crate and the lighter 4 kilogram crate. Okay, so it's asking, is subjected to the same net force and the same acceleration, is subjected to the smaller net force and the same acceleration, is subjected to the same net force and a smaller acceleration, is subjected to a smaller net force and has a smaller acceleration, or E, none of the above. George, since you were wanting to do this question, don't answer it immediately, but try and set us up. Like, how do you go about thinking about this?
Well, the first thing that I looked at was the fact that the rope is negligible, how you said. And it's very important, because if not, then you'd have to be taking into account relativity, and you'd have to be looking at crate A compared to the rope compared to crate A, the person, all that. So that's the first thing to kind of pull out the way. Next thing, I'm trying to see how to say it without giving away the answer on this one. Try to look at the weight a little bit more. Focus more on the weight and the normal force. So over that, I don't want to say too much.
You can just go ahead now if you want to.
All right, so it's going to be smaller net force and has the same acceleration.
Okay, and that's and walk us through how. So I'm starting to see where you got it, but so like explain.
All right, let's go ahead and reread the question. All right, so a woman pulls on a 6 kilogram crate, which is in turn connected to a 4 kilogram crate by a light rope. The light rope remains taut. Compared to the 6 kilogram crate, the lighter 4 kilogram crate is subjected to a smaller net force and has the same acceleration. So it's getting pulled with the same force at the same time. And since they're both going to have the same weight, the person's going to be pulling at the same acceleration, considering both boxes, at least the way I saw it.
Yeah.
So the weight on the smaller rope would require less force, but then again, it would still move at the same acceleration because you have 1, 2, box 1, box 2, the rope, and then the person with the other rope, right? So the tension between box 1 and box 2 is kind of out of the question. So the acceleration is going to be the same, right? But the normal forces for each one is different.
Yes.
The weight is different. So even though horizontally speaking, the acceleration is going to be the same and vertically too, but you guys get my point on this one. It's more about the horizontal when it comes to the acceleration, and then looking at the net force, I saw more of the weight. That's what I'm
Yeah,
looking at.
I agree. I like the way you're thinking, because even though you're not using the formula, it totally makes sense how you're explaining it. But basically, it's like we're using the second law, which is mass times acceleration. Acceleration is constant, as George is saying, but we see the 4 kilogram, it's less obviously than the 6 kilogram. So if we multiply that by so the mass by acceleration, we get less smaller net force, but the same acceleration.
Yep.
Okay, yeah. And the key to that is recognizing that the acceleration is constant, because from there you can see and just compare the two variables of mass. So, all right, perfect. George, I love the way you dissected that, because like when I look at this question, I had like the same thing as you. I'm like, wait a minute, like it takes you a second. So yeah, you explained that to me perfectly. You helped me understand it a bit better.
So you have to think about it as separate components, but at the same time, same component.
All right, so now we'll just look at some chapter 5 questions, and we'll just run that through. Again, we all have stuff to do, so we won't take too much of each other's time.
No worries, no worries. We're already about 15 minutes into this one. I'll go ahead and set another timer so that way we don't make the video too long either.
All right, perfect.
Gotcha.
All right, now we're looking at chapter 5.1. Ooh, this is a diagram we saw in the example.
Yeah,
so if you guys have
this
done
was
it.
the harder one.
I remember this one. All right, so I'll read it out loud. A car engine is suspended from a chain length ring to 2 other chains. Which of the following forces should be included in the free body diagram for the engine? I would immediately say T1, but yeah, because the ring would have all 3. It'd be like T2, T3. I'm sorry, it'd be like cosine of 60 T3, because I can actually annotate this. So it would look something like, and then ignore how bad this looks. I'm using a mouse, and this would also be 60 degrees because like geometry. And then you could find out the components for T3 and then for T2, but this is for the ring, right? For just the engine alone, I would say like T1 and then like gravity.
Yes. And also the direction that the net force is going in would affect it too. Because we had an experiment in our lab in which we had a ring just like that, but it's flat. And we have a weight on each arm, right? On each single T3, T2, and T1, we have a different weight. And depending on how the chain was set and the angles of each side, it would end up pulling it to the other. So that's why I agree with you on that as well. It's just a different way of looking at it.
I know, I'll Uber. It's fine.
No, it's fine.
I know.
Take my car and I'll Uber.
All right, so Maria, do you have any input on this one?
Well, now that I'm remembering, yes, we did this on the lab as well. But just by looking at what's going on the picture, we see that T1 is the most affected by like the weight in that specific direction. So if we draw a free body diagram for that, we would just take into consideration T1 because of it's the one that's being affected the most with the weight
I would say
and direction. So that's what we're trying to explain.
The most important component of
the
this
case.
question for me, at least, was exactly what Sergio explained at the beginning there, which is seeing that T3 is at an angle, and that same angle is corresponding to the x-axis, either if you place it at the top or at the bottom. So therefore, you already know the components of T2 and T1. Theoretically, you would know the component, the x component of T3 as well. And if you know the component of T1, then you know the y component of T3 as well. They're being able to figure out therefore T3.
Yeah, and that would help for the ring. That might actually come up in like the next following question, if I'm not mistaken. But let me clear. So I think for the car,
test.
yeah, absolutely. So are we feeling A for this? Just for the engine?
Yeah, I agree.
Okay, I would say A as well.
Yep.
Clear my drawing, and we're gonna check right now. It is A, right? So the only like major force acting upon it for this one is T1, then like, you know, gravity as well. But like that's like the force from the free body diagram. All right, so now we're looking at this one. These are fun, right? Because you have to take angles into account. I'll read through the question and we'll talk about it. So a cable is attached to a car attached to a car holds the car at rest on a frictionless ramp with angle alpha being less than 90 degrees. So this is less than 90 degrees. The ramp exerts a normal force onto the car, depicted here. How does the magnitude of the normal force compare to the weight of the car? So we can essentially draw a free body diagram, but let's get a pen out.
Yeah, for me, that's the biggest part about this question right here, at least when I did it, was the free body diagram. And just making sure that that I understood the fact that the normal force was going to be parallel to the ramp. So understanding that, perpendicular, I'm so sorry. So understanding that, then I can see the fact that that the weight is going to be at an angle. And then just figuring out the components of W, you're able to answer this question.
So if we were trying to do normal force is essentially, if we were to do this, it could be like the sum of F of Y equals to normal force plus whatever weight is. So if we look at its components, would we say, okay, so this is equal to this. Would we say sine of theta W is equal to?
Yeah, because we'd be using it as a y-axis.
Yeah. So, and would that be positive or negative? Anybody? I think it's negative.
Depending on how you arrange the angle and arrange your axes, but we could do negative since we have the normal force being positive.
So it does. So okay, so we're looking at it like this, and we were to use alpha as our constant. I'm sorry, it's W. Negative sine W. Sorry if I'm writing weird.
Much calculus for it.
So I would say that it would equal to. This is my knee-jerk response. I don't know if I'm doing this correctly. This is kind of how I'd look at it. Having normal force equal to the weight times sine of alpha. Because since weight is at an angle. Yeah, I would go with that. But I would kind of lean towards E.
Me personally,
maybe D. But I'm sorry, I didn't mean to cut you off.
No, you're good. I was saying, me personally, I would lean towards C. And the reason why I was just kind of thinking about it a little bit, you know, something on an incline is either easier or harder to pull.
Exactly. Yep.
Therefore, one of them needs to be either greater or less.
Yes, and also the fact that gravity is going to be acting on the weight as well, pulling it more down to that side. So the normal force would have a lot more to contend to. I don't know. That's just how I see it.
And then one thing, I'm actually starting to agree with you guys, because one thing is, no matter what, the sine of any angle that's less than 90 will be less than 1. So let's say this were like 0.6. 0.6 W is most likely less than. Wait, actually, no. I'm sorry.
Factual. It's factual.
Yeah.
It would be less than N. So
Yeah.
therefore, I mean, a good way to think about it is if you pull something up a hill, it's harder than to pull something down a hill.
Yeah.
Exactly.
So
That's the
if
way I look at
you're
it.
pulling it up the hill, then for this case at least, N would have to be less than W.
Okay, so
Mhm.
what are we going for?
I'd go for C.
C.
Yeah, I'd go for
Yeah.
C as well.
So
Yeah.
we're gonna check right now. So we looked at that and you guys proved it logically and I went with it mathematically and we arrived at the same answer. So I'm feeling pretty good about that. So let's see, and it's C. Great job,
Got it.
guys. I was already on the wrong track, but you guys steered me through it and then we were able to prove it with, again, logic and math. So I think we're in a good spot. So now we'll look into the next problem. I've never seen anyone like this, so this should be funny.
Yeah,
A
right.
traffic light of weight W, as shown here, hangs from two lightweight cables shown. Each cable hangs at a 45-degree angle from the vertical. And what is the tension of each cable? All right, there's definitely a formula for this that could help. We could split this up into components. I don't know how I would dissect this normally. Anyone have any ideas?
I think you'd have to make it on each their own little axis and then calculate them individually. Then after that, put them together.
Or you're saying make different free body diagrams for both?
Yes.
Okay, so let's look at it like that. So you would have, let's say we're doing this one.
Mm-hmm.
We would have this 45-degree angle, right? And so this is 45. Ooh, yeah, because if it's 45 here, it's 45 there to make a 90-degree. So this would be 45. And then the weight of the traffic light is going that way, right? We're in agreement with that.
Mhm.
So if we break this up into components to get this angle,
Well,
this,
you could do another 45-degree angle right there.
yeah. But yeah, so if we did this as 45 as well, we still need to get the components of this line of, let's say this is tension, right?
Well,
So-
I wouldn't do it like that so much. I would, so the same way that you have the tension to the right on the top with a 45-degree angle, I'll just do a tension to the left the same way. So it kind of be like this, and then with the one on the bottom.
So you're saying
So more like a Y.
to
Yeah,
do
kind of
this.
like a Y. Yeah.
I was gonna do them
Okay.
separately, but this works too.
Yeah, I was thinking of separately too.
I feel like here you'd be able to knock two birds out with one stone now.
I mean, my plan was probably to just make this one negative of whatever I got here. Actually, no, that wouldn't work. I would do a negative X component. So let's just look at that, right? So this would be cosine of 45t
Yes.
plus, let's do T1, right? This is
Sine of
T1,
45.
this is T2, right? Or we can just call it those.
Yes.
These, like on this side as well, we just do a dot, 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 right? This is also 45, this is also 45. And we're gonna make an x-axis here, right? Just as a general rule of thumb. So if we were to do f of x, yeah, so let's do f of x of 1. So we would have that equaling to, actually no, if we're looking for the vertical, right? The tension of each cable, actually never mind, we were looking for both. So if we did the horizontal tension, I think we should split this up.
That's what I was
We
thinking
could.
about at the beginning. To like it'd be easier to digest if we had one side and we just got to factor the other ones in.
Yeah, maybe we should try that. If you guys want to maybe like do this on a separate piece of paper while I try to solve it here, just so we don't waste too much time.
Already on it.
All right, yeah, okay, we'll get this. So I'm actually gonna pull out the eraser. I'm gonna do this in pieces.
So we'd have 180 minus 45. Not sure. No, I'm not sure. 180 minus 45, right? Yeah, so we'd be looking at 135. Should be. Yeah, so cosine would be negative.
Will we use cosine or sine instead?
For the x value, you could use cosine 40.
And for the Y, you sine.
Yeah.
Yeah, so what I'm looking at right now, guys, is I'm looking at it being b, y divided by square root of 2.
Okay, I can see that.
reason why is because if you do for T1, which we had mentioned T1, we do cosine of 45 plus sine of 45. We arrive at 2 square root of 2 divided by 2. Yeah, 2 square root of 2
and then
divided by 2. And then I do
That's
the same
also
thing
the
for the
trig
other one.
function. That's also the trig function for the 45 degrees right there.
Yeah. Then I do the same thing opposite for 135 degrees, so 180 minus 45. So I do it for the 135, and then that's how I write my answer. W.
Okay, I like your reasoning. I honestly, I don't have objections with that because that makes sense to me. I'd be interested to see and like try and confirm what he said.
Hey, I hate the unit circle. It took
No,
me a while
I
to learn
hate
it.
bro.
So the fact that I'm able to use it when I do, it's very rewarding.
Yeah, you're right.
Yeah. Took a bit
Okay.
to remember
I like
too.
that a lot.
A lot, yeah.
That would make sense. It would be radical square root. Okay, yeah. Do you have any objections? Because I'm down
Good
to
with that one.
No, I don't.
You're right. Impressive, George.
Oh, there you go.
Let's go.
Get
All
it.
right, that was really impressive. So we'll now look at the next one. Ooh, a pulley problem, our favorite. So a cart with a weight 1 is attached by a lightweight cable to a bucket weight 2, as shown. The ramp is frictionless. When released, the cart accelerates up the ramp. Which of the following is the correct free body diagram for the cart? Not the bucket, but the cart. Just looking at this, it's weight 1.
Can't be straight. Hold on, I got a pen real quick.
Either A or C, because N and T have to be parallel to each
Yeah,
other.
they have to be perpendicular.
I mean perpendicular. I'm sorry, I keep saying that.
Yeah, I got you.
It's either
So-
C or
Can't be
D.
that. You said C or D?
Yeah, I say C or D
It's gotta be
because
C.
we have acceleration.
I agree.
And
There is an
the- and-
acceleration. I think it's C because, like what I think George said, the normal force needs to be perpendicular to the platform,
Yeah.
the ramp.
I was about to say since it has a ramp, it can't be either of these because that's not
Mhm.
perpendicular and it's
And
only
we know it
having a
can't
normal
be-
force go up.
Yeah. And we know it can't be A because A doesn't have acceleration. So we know
Facts.
that it needs to be perpendicular to the ramp or the surface and it needs to have
And show
acceleration.
tension. Mhm.
Exactly. So I have a feeling it's C, and I feel like we're pretty much in agreement there.
Mhm.
It's 2 and
So we'll take a look right now. Oh,
Oh,
okay. So let's talk about this.
well, at least we were in the ballpark.
Yeah. So let's think about this. So a cart weight is attached to a lightweight cable shown. The ramp is frictionless, and the cart accelerates up the ramp.
hold on. I think I got that one. I think the reason why it's not C is because C shows the acceleration M1A as if it
Ooh,
was the
that's a
acceleration of the
force.
cart, but it's not.
That's
It's
also,
supposed
I believe,
Because
M1A
it should
is
go
an
off the
acceleration
bucket.
of force.
Yes, M1A
Right.
should go off the bucket because
It
the
should go
bucket
off
is going down instead of, in the other direction. That's what I was thinking.
I think that's the missing link right there.
Okay. So we do understand how we got that wrong. So
Mhm.
I'm happy with that.
But we were in the ballpark.
So it'd be the
Yeah,
same thing,
exactly.
but just it wouldn't be included.
Yeah.
Mhm.
So I think it's
But
fine.
if they
that
were
we-
asking for bucket, I think for sure it'd be included, but it'd be going down instead though.
Mhm. All right. So really good job. We made a small mistake, but I think we understand why we did it. I don't think we get that wrong again. So great job, guys. Now we can look at 5.5, another pulley problem. So let's try and redeem ourselves here.
All right, let me try to read this one. Let's see
Go
how this
ahead.
goes. A cart weight W1 is attached by a lightweight cable to a bucket weight W2 as shown. The ramp is frictionless. The pulley is frictionless and does not rotate. Okay. When released, the cart accelerates up the ramp. So in that direction, and the bucket accelerates downward. How does the cable tension T compared to weight?
So
Interesting.
if we're going to look at this, let's say we're doing the free diagram for the bucket, right? Because weight 2 is from the bucket. If we were to do the free diagram for that, we'd have,
Would tension have to be less in order for it to move at all?
it would. But we'll also, that's already our answer, but we can look at the diagram as well.
Word.
So let's say we have our tension, right? And our weight 2 of the bucket. again, you can already tell that weight 2 is going to be bigger because it needs to accelerate. They won't be equal because let's say if we're doing f of y2, if they were equal, the net force would be 0, right? We agree with that? It would be
Agreed.
T plus negative W2 would equal 0. But that is not the case, because if it was 0, this would be at equilibrium, it'd not be moving. So if we know that T plus, sorry, this is negative W2 would have to have a greater force than 0, right? Or actually, since it's downward, it'd be less than 0, because this would be a negative force. It'd be going down. So if it's less than 0, if we solve this, it'd be T is less than the weight 2. If we're just solving this logically, right? And that makes sense because we have a downward direction. So I'd be inclined to put that T is less than weight 2. Let's see.
Yeah, me too.
Agreed.
All right, let me clear my drawings and then we'll check. And it's C. So yeah, we did like 5 and 5-ish. You want to do like an extra problem here, find a hard one and see if we can solve it for chapter 5.
I was actually looking at question 8. Reason why is because it's kind of like the backwards question of the answer we just got.
Okay, we'll tackle it right now. So a toboggan. Okay, so a toboggan, which is a slide of a weight W, including passengers, slides down a hill with an angle of alpha at a constant speed. Which statement about the normal force of the toboggan or the magnitude normal force is correct? Okay, so knowing this, we know that the the acceleration is constant. So the acceleration is 0, speed is constant. I would say that weight would be greater than normal force, because if not, it wouldn't move. Yeah, so weight has to be higher than the normal force.
I saw the look on your face of realization when you got it. You're like,
yeah. That's the thing. Honestly, I find conceptual questions a little tricky because I'm like, it'd be so much easier if there were numbers to like prove that what I'm saying is correct.
But it's cool because when you have the conceptual questions down, then the number questions make sense and you're able to see mistakes. Like, oh damn, like no, this makes no sense at all. Why is this number 2 here? You know,
I totally agree. I totally agree.
Those are the good questions.
So yeah, I would say that if anyone wants to fight me to the death about it, go ahead and tell me I'm wrong. But I would say that the weight is greater than normal force.
Yeah, I agree with that too.
That's like an object with no mass sitting at the top of a mountain at an angle. It's not going to move because it has no mass.
So I would say C, and we'll look at it right now. Oh wait, yeah, it is C. Good job.
Get it.
Good stuff. Good stuff.
Got it down.
Let's see. Oh, whoops. I need to fix this. Clear drawings. And let's just look for one more and then we can like leave because I think George has work kind of soon.
Yeah, clocking in 25 minutes.
Oh, okay. Yeah. We'll do one more and then we'll let you run.
It's all right, man.
Don't want to get you late. Let's do a circular motion one. I know very little about these.
Okay. That's cool. That's a good one.
All right, so a pendulum bob, which I'm assuming is like the thingy, whatever, of a mass m, is attached to the ceiling by a thin wire of length L. The bob moves at a constant speed in a horizontal circular radius r, with the wire making a constant angle beta with the vertical. The tension in the wire, and then it has all these things. So I know I'm not too great at these, but if it's asking for the tension in the wire, I would say that it is.
You already answered this.
I already have.
Yes, you did.
So if it's moving, oh, wouldn't it be equal? Because it's.
I would say the tension is greater than mass times gravity.
Oh, I guess so that it doesn't fall.
Because as it goes around, its tension is, I guess, I don't know how to explain it, but as it's on that edge right there, hold on, let me see if I could. As it's over here, that's one of the places in which its tension gets greatest. And so having mass and gravity applied to that as well would definitely make it greater.
Okay, I'm starting to see. So like what's keeping it in the circular motion is the fact that the tension is greater than the other forces.
Exactly, and the angle too. It depends on the angle.
I
All
agree.
right, George, you're gonna say something?
Nice. I agree. I agree.
Okay. Okay, so like the general rule of thumb there is it would be greater than mass times gravity, because I mean, like if mass times gravity was greater, I think the the wire would kind of snap.
Yep.
Yeah.
So the fact that it's keeping in this circular motion is the fact that the tension of the wire is strong enough to maintain the circle. So it's getting
Going.
pulled. Wait, what? No?
Yeah, exactly.
Okay. So the fact that it's going in the circle is a result of the tension restricting the ball's movement. Because if not, the ball would just fly off.
Randomly.
Yeah. So the tension of the string.
It would
pulls
it,
this-
it would have that. Remember when we did the acceleration? It would go over and under. It
Yeah.
would be one of those.
Oh, okay. Okay. All right. I think I understand that. And I mean, I think with that, we've gotten a decent amount of examples under your belt. I know we have other things to do. I'm
So
going
we
to stop.
we got
Oh,
it
no,
right.
no,
It
no.
was no. I just want to make sure we got it. It was.
Oh, for A,
Yeah.
we're correct.
That's
So
good.
good job, everybody. I'm going to
stuff.
quickly stop sharing my screen just so we can like say hello to the camera. Again, it's I'm Sergio, there's Lordson, George, Maria. And yeah, that's a video. I'll send all of you guys this in the group chat most likely. I'll download it and then I'll post it onto my YouTube and then I'll send that to you guys, the link.
Yes, for
So you'll
sure.
be able to submit it individually. Sir, if you're wondering, I will count myself as leader, even though we're all going to submit it. I'm going to make sure to put all of our names in the thing and then we'll be good. Okay.
Yeah, sure.
Okay.
All right. I'm going to
Thank
All right,
you,
you guys.
Sergio.
Thank you, Professor.
Peace out, everybody.
Bye.